Adina from Escola Polytechnic, France.
Yes, it's F5.
It's about reliable motion planning.
Hello. So today I'll talk about some reliable motion planners, which can be then used in application as autonomous vehicles. I will show some literature review, some algorithms from literature review, which are at the core at the proposed reliable motion planner. I'll present the contributions on this thematic, and I will show a small application, and I will finalize with conclusion and future work. Thereby, our goal is to have a motion planner that is reliable, meaning that we know that in an autonomous vehicle we have a mission which is given to a planner level, and this planner level it is at the core of the autonomous property of the vehicle. And this planner will give some reference to the control level, which will lead the robot to accomplish the mission. Thereby, at the planner level, we have two ways of planning a trajectory. One way it is to generate a set of points, and afterwards the controller level will apply some controls to follow these points. And we have the motion planning, which will take into account the dynamic of the system, and we will obtain the trajectories and the controls which are attached to the set of these feasible trajectories. So our focus is on a sampling-based motion planning algorithm, and in the literature, we are interested in particularly two of them: the rapidly exploring random trees, which are denoted and known as RRTs, and the optimal RRTs, which are known as RRT star. The idea of these two motion planners is that they are based on trees, and they are exploring the map in a random way rapidly. So the difference, though, it is that the RRT do not converge to an optimal path, while the RRT star will converge to an optimal path. And this happens because the way of this can be found in the way the trees are constructed. The RRT is like picking a random state to the discretized map. We'll choose a near vertex from the tree, and we'll generate a trajectory. And we will do it is an iterative algorithm which will be iterated as many times as the user will want. But the RRT star is like updating the tree, meaning that if you have a state at one iteration in the tree, and this vertex has a father, we will search for a better father in the tree with a smaller distance. Okay, but we also want to take into account the uncertainties. Why? Because we want to have a reliable motion planner. And this kind of idea was already proposed by Pepi, and the name of the motion planner is BoxRRT. Box because the uncertainties are taking the location uncertainties are taken into boxes, into intervals. And the main idea is that if we have a differential system which shows the system's evolution with piecewise constant bounded function for the control input and the states, measurable states of the system, denoted by S, the main idea is to find this sequence of control which will lead the robot from an initial set of states to a final set of states while avoiding the obstacle if such a path exists. What we have done first, we took to this BoxRRT motion planner, and we improved it. But in fact, what it was done, we used a library, DyneEBEX library, proposed by Julien Sanoto here in the room. And this library, in fact, combines constraint satisfaction problems, IEBEX, it's integrated in IBEX, with guaranteed integration methods. And the simplification of this DyneEBEX, in my case for this motion planning, is that I was able to use the temporal constraints implemented in DyneEBEX, which were very easy, meaning that if I wanted to see if the states are in the state space, I only used this kind of inclusion, verify this kind of inclusion. If, for example, has crossed, I will show later the difference between DyneEBEX and how Pepe used the wrapping effect for the has crossed an obstacle. Or if I want to state that a state finished in the target, I have this kind of temporal constraint which needs to be verified. So, how does this BoxRRT works? Let's consider the discretized map only for the representation, okay, only so we can see a representation. We have the initial state in orange and the final state in blue, and we have some obstacles. And below, I represented like a tree of possible trajectories, which has as initial node only the initial state. This one, I put it here only for the representation, okay? The first step in the iterative algorithm, which is composed of three main steps, it is to pick a random box on the configuration space, okay? Afterwards, we need to find the closest node in the tree. Here we are at the first iteration, so it will be the initial state. And the third step, it is to integrate the system with a control and to find a new state, thereby a new node in the tree. And here, for example, if we would have used the property of showing if a state has crossed an obstacle, if we have used the wrapping effect, we will have had like an interval hole for this set of trajectories, and maybe it will have had an intersection with the obstacles, and this state wouldn't be feasible. But in this case, because we have used the temporal constraints, we can see that the state doesn't intersect with the non-admissible with the obstacles, so we can keep this state into the graph of trajectories and into the tree. And we will repeat these three steps until there are two possibilities, or we found a path and we stop, we will use that path, or we fix a number of iterations, and after this k number of iterations, we will see what path the algorithm found, if such a path exists. BoxRRT works well, even implemented in DyneEBEX, but also the one proposed by Pepe. And what we wanted to do was to take into consideration the dynamics, the evolution of the system given by a differential equation. The same, the control input was considered as piecewise constant bounded functions. And we wanted to find a sequence of control input which can lead the robot from an initial set of states to a final set of states while avoiding obstacles, but in an efficient and near optimal distance. The path needs to be an optimal path. And the contribution here was to combine this RRT star proposed into the literature with interval analysis tool, meaning that we implemented the RRT into DyneEBEX and we took all the initial and final uncertainty on the location into boxes. This is why the name is BoxRRT star. So how it's worked? The same, the discretization map, it is only so I can do my representation of graph of trajectories. And here I have the tree. I consider I didn't design any obstacles because it was more easy to explain, but the idea is that if I cross an obstacle, that state will not be taken into consideration because we'll have collision, maybe. So supposing that we are at a certain iteration, we have the initial and the final set of states. And on the tree, we can see some values. For example, the 10 values here. This is the distance which we have starting from S0 to arrive to S5. Okay, so the first step, it is to pick a box randomly on the map and to find the nearest vertex in the tree. This is the random box. We found the nearest state, the nearest vertex. We integrate the model with a constant control input, and this input can be randomly or can be designed according to a desired obstacle or behavior. And we obtain as solution this state. This is dashed because the next step, in fact, here I put this state in the graph, but it is temporarily put in the graph, okay? Because we need to find a better parent for this state here, okay? So what we do, it is like we are looking for all the vertices in the tree, which are within the area of a ball of radius, and here we are taking the value given in the original RRT star algorithm. And we are looking at all these vertices, all these states. We need to see if by integrating the model from this state to arrive in the new one, we will arrive in this state with a smaller distance for the path. So we are starting to look for the better parent for this temporary state. When we integrate these two nodes, because these two nodes are the ones available, okay, within the ball, we see that we have some states, but because we are working with boxes, we will not obtain the exact initial state, okay, the black one. It will be like intersected to this black state, okay. So we will have like 3 boxes, 3 new states. And we will choose the one which has the smaller distance. And in this case, this one will have the smaller distance. So we'll pick this one. And we will replace the first temporary SN state in the tree with this violet state here. And we will obtain this one now. And the other one will be erased from the vertex. And this is not a problem because at this point in the algorithm, we want to introduce states in the graph of trajectories. We will not modify nothing in the graph. So we found a better parent for the state which was in this region. And now the goal is to see if, starting from this state, this vertex which is included in the tree, we want to see if we can find him a child, and if the distance from this new state to the new possible children, to his new possible children, can be done with a low-cost distance. So we are doing the same thing. We are integrating the model starting from this SN state. The same thing here is the catch, is that when we integrate, we will not obtain exactly the state which is in the tree. Okay, we will obtain something which is near this state in both cases, and we will choose the one which has the smaller distance. And in this case, this is the one. And what we'll do, we will keep this new state, but we will also keep the old state from the graph of trajectories. And we will do these iterations until we decide to stop, because we want to have when the algorithm found the trajectory, we stop, or we impose a number of iterations, and then we stop and we see the obtained path. We applied the two algorithms on a simple car model. We have the position on x, y, and the orientation theta. And we have as control input the speed, the linear and the angular speed. And the L here is a distance. It's a parameter of the model. We designed a control, and we said that we want, at one point, when we need to integrate the model from the nearest state in the tree to the random chosen to the random box. We want the robot to orient towards this goal. Let's say that this is the goal, and for 1 second, and afterwards we want to go ahead for another second. And when it stops, this is the S new, the new state which we introduce in the graph of trajectory, and the vertex which we introduce in the tree. So we thought of, we took the labyrinth map environment usually used for this kind of motion planners, and we want to stop after 10,000 iterations. And what we have done, we used the BoxRRT with a random control, with the design control, and we applied the BoxRRT star with the design control. Here, it is for a specific, we simulated each motion planning once, but if we simulate each of these motion planners for like 50 times or 100 times, the ideas will be the same. Meaning, when we don't have a control, a specific control, it is randomly. The path, we can have like places which the dynamics of the robot is incapable to do. We have a number of seconds. Here it's low, but usually it is high. The cost, it is high usually, and the path nodes, meaning that how much states I have during the path, okay, it is the higher one. When we apply the design control input, when we orient towards the goal and walk straight ahead, we have some improvements at the level of the cost and the path nodes, number of states in the nodes, how many times we apply the controller, in fact, and the CPU will increase a little bit. But when we apply the BoxRRT star, what we see is that as we expected, the cost will be the lowest one. The states on the path are the lower one, which is good. It's what we wanted. We will apply the control not as many times. So, from a robotic point of view, this is a good fact. But from the CPU point of view, this is the more expensive. And why? It is normal, because during the algorithm we will integrate the differential equation 3 times at what iteration, while for the BoxRRT we will integrate only 1 time. So we proposed 2 motion planners which are reliable for a simple car model, but it can be extended to more complicated models. What we are doing now is we are trying to validate these motion planners on real-time applications, on real mobile robots. And what we want to do is to improve this version of BoxRRT star, because we are working with boxes, and because of the pessimism of this interval analysis, we can have situation where if the uncertainty is too big, then the states will be too big, and we will not be capable to arrive in the final set of states. And also to take into account uncertainties related to the model and to the sensor information. Thank you.
Any questions?
Yeah, and just the slide before the last one, where you have the results. I'm just wondering, the image to right.
This one?
Yes, using your approach. Is that the optimal path? Or there's something that's optimal in that?
It's optimal path in terms of distance, yes.
Okay. So how come the BoxRRT doesn't give you the optimal path as well?
Because of the structure of the algorithm. Because this kind of algorithm will update the tree. So the RRT, we have a tree, okay, with vertices and with edges. The vertices are the states and the edges are the trajectories. So the BoxRRT has 3 steps. We need to choose a box, okay, to integrate the model to have another state in the tree, and we'll repeat these 3 steps. The BoxRRT star, it's introducing a new state into the tree, okay, but it's looking to change its parent. So we will modify the path, in fact. This is why we will obtain an optimal path.
Professor Nasser.
Yes, thank you. I was wondering whether the choice of the control input
Yes.
may have an impact on the solution.
On the findings. If okay, so we can see the impact of the control only on these 2 cases. If we had another control, the difference will be that here we will have not such a good path. Okay, the path will be not like going towards the goal. We can see that it goes towards. It will be more like this one, but smooth, in a smooth way. But for the BoxRRT star, I think that it will be like this. Finally, after a number of iterations, the modification into the tree will do the job. So we will.
When you say design, what do you mean by design?
Design is like we thought of this 2-step control.
Okay. So do you have an idea about the generalization to optimal control, or just locally, or is it not relevant?
No, it is relevant, and we haven't done that because we are waiting for some improvements from the DiniBex library, and it is ongoing work, to say like that.
How would BoxRRT star compare with BoxRRT if you were to reduce k, so the runtime would be roughly the same?
Yes, it will be the same. It will not be the graph, the path. It will not have this kind of shape, okay? But in terms of costs and the path nodes, this one will be smaller than the BoxRRT.
The same CPU.
Yes, yes.
Do you try to apply such a method also in easier environment when you have
Yes,
less
of course.
or no
Yes, when
obstacle? Because in this kind of situation, you expect to obtain straight line.
Yes, of course.
And when we test mission planning tools, we start by
That
environment without
obstacles.
obstacle, even if we expect after to obtain
Okay.
good results when we have a complex situation.
I haven't shown that here because I thought, okay, let's present the labyrinth map. But yes, if we don't have an obstacle, okay, the path will be like straight ahead to the goal, but it will be straight ahead for both BoxRRT maybe and BoxRRT star if we will decide to stop when we found the first solution. If we'll iterate, okay, for k iteration, we will see that the BoxRRT star, it will be exactly a straight line. While the BoxRRT, okay, it will be like a straight line, but it will have it will not be straight. It will converge to.
Any more questions? Okay, Just a quick one. So your obstacle is static.
Yes, it's static.
So if it's dynamic obstacle moving once, can this method be extended to?
We need to do some modifications
Okay.
for the dynamic, but there are some other versions of RRT. The name is RRTX,
Yeah.
which is dealing with this kind of issue with dynamic environments.
Okay, thanks. Okay, thanks. Sorry.
Yeah, just one question. Can you kind of eliminate, just to name a suggestion,
Okay.
areas with no way out? For example, like in this, the area on the right, one which is kind of white,
Okay.
in which the algorithm has, where there are no boxes. This area seems like an area where with no way out, so an area which could not be explored because it's for sure for any box there is no way to go to the destination. So can it be just eliminated? There are many areas which could be simply eliminated because they don't lead to the result.
Between us, this can be a good idea, but when we have a map, not usually. So we have a map. We have a mission. Okay, we will give to the robot this mission, and okay, we can cut the map, but the idea of this kind of RRTs is to explore the entire map, even if there are places where maybe it's better not to explore them because we know that we will not go to in that region.
Okay.
But maybe we can think of implementing a stuff like this. Yes.
Okay. Thanks a lot.
Thank you.